Alright, welcome back. So we were getting down and dirty with memory. We learned about pointers, we learned about how memory is arranged in our programs, and let's keep going. We're going to talk about something called the heap, which has an interesting name. I guess a heap just means a whole bunch of something. Well, it's going to be a spot in memory where we can put a whole bunch of whatever we want. So we want to make variables that live forever. We know one way to do it. That's through global variables. So the way that we know how to do that right now is globals, but we're also going to learn about this thing called the heap. Well, the heap.cpp. So normally, if you wanted to make a variable that lives for the life of the program, like here's foo, it has an int x, and it only lives for the life of foo. So it's what's known as a local variable. The alternative is to use global variables. So int global var, or this is a global var. You can have it set to whatever you want, 3 I guess. And this variable will live forever. And you can use it anywhere. So you can print it out in main, you can print it out in foo. This is a global variable and it lives outside of any function. So that's one way to have variables that can live forever. Dun dun dun. The heap, though, is a different way. So all global variables are, I guess, allocated is the word. It doesn't really have to be in quotes. Are allocated, they're made for you. Right as your program starts. And they last forever. The one downside with globals is that they live forever. Maybe you needed a very large array and you only needed it for part of the program. That's a waste of space. You'll have it sitting around forever, this giant array, and it's just taking up memory that you don't need, because you might not use it for the entire program. You only need it for part of the program. Okay? So that's globals. There's a new spot in town. There's a new place in your program that we haven't talked about yet. It's kind of the last hidden thing. So there's this thing called the heap, and let's get into that. So this on the right side is what your program looks like when it's loaded into memory. At the low addresses, like starting at 0 and working its way up, like addresses get bigger as you go down this diagram, the first thing that you have is called text, and that is the actual machine code instructions for your program. And obviously that part is read-only, so that you cannot modify the instructions that your program executes. Otherwise, you'd have a different program. That is not okay. They used to allow that in previous programming languages, though, previous operating systems. That was a bad idea, everybody decided. Then the next thing, the next space in memory, it takes up a chunk, if there is some, is your global data. So then you have your globals. since they have to live forever. And then there's the stack that we know about. I'm going to skip the heap for just a second. There's the stack, and it lives in this entire chunk, okay? It's fighting with this thing called the heap, and it's growing. It's growing towards smaller addresses. We say that the stack grows down towards the lower addresses, even though this picture is kind of in the wrong orientation for that, okay? Function stack, where all your local variables live, takes up a portion of the third chunk of memory. And the stack goes down. Okay, there's one more thing called the heap, and, well, let's talk about it. So this global space is completely separate from the space for local variables, for the stack. So for example, if I say foo in main, my function call stack might look something like this. Inside of main, I have no variables, but inside of foo, after I call foo from main, I'll have an x that belongs to foo. And then there's the global space, which is like way over here, a different section of memory, up here, not down here in the stack. We have those other things. We have, this is a global var and huge array. So I'll just call them, I don't know, huge array. I guess it's a very long array, right? And then global var. And those exist over here, and they exist for the life of the program. So those are your globals. And then the stack holds local variables, like main, all of its local variables, everything that main calls. And it's going to grow and shrink, of course, as functions get called and functions return, because eventually foo is going to return, and all the space that was needed for it is no longer necessary and can go away. Okay, the final piece of the puzzle is this thing called the heap. The heap fights for space with the stack. And it grows upwards and towards higher addresses. And it holds what's known as dynamically allocated things. And this entire little subsection of this lecture is going to be defining what this idea means. What is dynamically allocated stuff? So, one last thing for this slide. The stack and the heap, they're fighting with each other. The second you call too many functions, or you allocate too many things on the heap, they will clash. The space is not enough for both of them, for a ton of functions and for a ton of dynamically allocated things. If they ever meet, then your program has run out of memory. And you'll get an out-of-memory error. It's a runtime error. It's one that you probably have not seen yet. It's kind of hard to do without this thing called the heap. All right. Let's talk about the heap now. So the heap is a place where you can create and destroy memory when you want to. Okay? So unlike globals that live forever, any memory allocated on the heap can be removed as well. And like globals, anything allocated on the heap lives between function calls. It lives for potentially forever. That is until the function, or until the program is over. But unlike globals, you can say no, I'm done with this. So here's a global variable, x. It lives forever. You can't get rid of it. But this thing called the heap, you can say, it's a separate place in memory, you can say, hey, please, make an int. And you get a nice shiny new int. Hey, make a double. And then you can also say, all right, I'm done using this now. Delete it. Delete the int. Delete the double. Okay? I don't know why the first one wasn't read. Whereas for globals, it's impossible to delete. So that's the main difference between the global variables inside of your program and the heap. With the heap, that memory can potentially live forever, but also can be deleted. Okay, so if this is not making sense, I'm going to give some examples now. Okay, so the first thing that you need to use the heap is this thing called the new operator. It's going to return a pointer to a type of something made on the heap. Okay, so this is, again, a lot of words. Let's talk about this. So if I say new, it's a keyword in C++, and you need to give a type afterwards. Okay, so new int, that is one expression in C++, and what this will do, if you say this in C++, how do I want to do this? Let me put it in the code font. New int, and new is the keyword, so it'll look like that. I guess they're both keywords. Returns a pointer to an integer that was allocated on the heap. Okay, so if you want to use that thing, you'll say int star. It's going to give you back a pointer, and star n, I guess, equals new int. And what this will do is allocate an int on the heap and give back the pointer to it. Okay. So here's what happened in memory. Maybe in main, on the stack, you said int n equals new int. And so the n, the pointer, lives on the stack. And on the heap, you said new int. So what it went and did on the heap was make one box in memory, shiny and new. It's a brand new integer, and it gave you an address of that. And n took that address, and now it's pointing to this place on the heap. Okay? So, just to drive home the point that this int got made brand new, I'm going to make it all shiny. Okay? And right now it's holding a random value. Okay? And you can set it as usual. You can say, all right, star n equals 42. And now suddenly it's 42. But this memory can outlive you. So let me show you that. Dun, dun, dun. Here's a function. It returns a pointer to an int. So here is my int star n equals new int. So make an int on the heap. And I'm going to return n as well after setting it to 42 and printing it out. Okay, so I'm going to call bar down here in main, and it's going to make a new integer on the heap, set it to 42, and print it out. So it should, in theory, just go and do everything that we know that a variable should do. Which is apparently nothing at the moment. What have I done wrong? Oh, I didn't save it. Sorry. There we go. Prints out 42 because it calls this function. It's like, yeah, it's a new int. It's a place that is an integer. I can set it to 42 and I can print it out. Okay, should be 42. But I'm also going to return back from bar this address, the address that was stored inside of n. I can get it back here. So bar returns back the address of the new int. And suddenly, I can reset that thing. I'll call it int pointer, reset it to 43, print that out. And suddenly, I have the same int existing across function calls like a global variable. Let me show you what just happened. So here's the stack. So main is trying to make a variable called int pointer. And it's going to set it to whatever the value returned by the bar function gives back. And the bar function, when it's called, makes a local variable called n, sets it to be a new int on the heap. So here's the n, and I'm going to draw this kind of all over again. So here's the heap over here. Same picture. It made one new integer. Maybe it was address 100. This held 100. And it sets it to 42 and prints it out. Okay? The reason that you can get away with all this is that this heap is a separate place. Once bar returns, you'll still have access to this memory so long as we return that address. So here we do it, right here after we print in bar, we return n back to main and set int pointer to be that. So this returns back the address 100 and sets it to be int pointer. So int pointer is now also pointing to this place on the heap, which has no name. Places on the heap are just referenced by their address. And so suddenly, even though bar has returned, there is no more stack frame for bar. N was a local variable, but it was just a pointer. This int that it set, that we really care about, was over here on the heap, and it lives for as long as we want it to. Okay? So it's a different kind of thing to the global variable space, but it's very similar at the moment. So we've made a place that can live forever across function calls. Okay, now we can get rid of it as well. So if you say delete n in C++, it takes a pointer to some place on the heap. It deletes that memory. So suddenly, once we're done with something that we made on the heap, we can get rid of it. Okay, so we can say something like, all right, and it's a pointer to a place on the heap, and we can mess with it, set it to 43, for example, print it out, and the second we're done with it, we can delete it. Once we say delete, it gets rid of the space, and you shouldn't use n anymore. Okay? That memory got reclaimed. Okay? So now we're done with the int we made on the heap. Let's delete it. Okay, so I'll say delete int pointer, because that's the address of that place we made on the heap that we would like to get rid of now. And so that will finish off our program correctly. Now, after this line, we cannot use int pointer anymore, because that place on the heap is no longer valid. So the beauty of this is that we can allocate and deallocate memory as much as we want, as long as we clean up after ourselves. So let me show you running out of memory, an example of that. So while, I don't know, for int I equals 0, I is less than. Let's start with 1,000,000. Let's say int star int, or I equals new int. So make a new int on the heap. Oh, we can't use I, sorry. Let's call it, I don't know, integer pointer, IP. Make a new int on the heap, and then stop. And we don't use it. So what this is going to do is it's going to make a 1,000,000 new integers on the heap. Okay? Oh shoot, I guess I have enough memory for that. Let's add some more zeros. That's more like it. So, it appears that I have just crashed this virtual machine because I've done this. So eventually, it's going to stop the program and realize that it had no memory because it ran out of memory. So I'm going to have to wait for this thing to recover itself, because right now it's trying to save all the memory to the disk. It's swapping out things, if you can see that at the bottom. So I'm going to have to pause the video and come back because it needs to hurry up and stop running. All right, we're back. So this program got killed, we say, by the operating system, and because there was no memory left. And so we made a bunch of brand new integers on the heap, and, well, we just didn't have room to store them. So you can make as many things as you want on the fly. That's another nice thing about the heap. Maybe we should put that on our list. You don't have to decide up front how many, and by up front I mean before the program begins, how many things you need to store. You can add and remove as necessary. All right, so back to here. Well, this is making a bunch of ints and then losing access to them. So how about I just make a bunch of ints and then delete them as well? Nope. Come on. Delete IP. There we go. So, I'm going to compile, gonna rerun, and this time, I really hope it recompiled. There we go. This time we can wait. It's just making an int, deleting an int, making an int, deleting an int, making an int, deleting an int. It will end, and it will not run out of memory because it just deletes what it just made and probably overwrites it. So there's a big, big difference, and you're allowed to delete things whenever you want. So that's super nice about the heap. You can, all right, I need an int, I want to make an int, and once I'm done with it, I will get rid of it. Okay, with that, let's move on to arrays. We can make those on the heap as well. So first we need to talk about what an array really is. When you say int arr 42, for example, this makes a local array. ARR by itself is really a pointer to the beginning of the array, and that's a little weird. So what it's doing is I had ARR, here it is, it was size 42, and so we draw it like this usually, but really what's happening is, say this is the array right here, it starts at address 100. Maybe the next element was at 104, 108. That's what arrays look like. So it's got 42 things in it. ARR actually holds 100. Boop. And so it's really just a pointer. And if you don't believe me, let me make this much smaller now so that it'll actually run on time. If you don't believe me, let me show you. So int ARR, this is a local array. It's not made on the heap or anything. I'm going to print ARR. Are you ready? That's an address. That's a pointer. Oh, shoot. Okay. ARR is a pointer to its first element? Are you sure? Let's give it a few values, 1, 2, and 3, and for its starting values. I can have some empty space at the end, that's fine, it doesn't care. Star ARR how much you want to bet that that prints 1? So ARR is just a pointer to the beginning of itself. Oh shoot, that's really weird. And the reason that I'm saying this is because if you want to allocate an array on the heap, you have to use pointers. New gives back a pointer. So let me show you the following. Int star p equals ARR. So I promised I was going to put those over here. There we go. P points to the beginning of ARR. Cout P of 1. I can use a pointer like an array. That's really weird, but these two, all these ideas together allow us to allocate things on the heap. Oops. Let me, if it ever lets me go back to the previous desktop, let me show you just quickly how you can do that. So AR1 is secretly translated into by C++, dereference ARR plus 1. That is the weirdest thing, but let me prove it to you. Let's say the same thing for P, I guess. So the ARR of 1, it's 2. Let me print it out. Star ARR plus 1. Yep, it's printing 2. Why? So the reason for this, ARR is the starting address of the array, and 1 is an offset. C++ knows to go 1 int later, not 1 byte later. It knows that because ARR points to an int, that you want the next int, not the next byte. That would like make things weird in the array. So, for example, if the array started at address 100, the next element was 104, 108, ... 1, 2, 3, ARR plus 1 is really a pointer to right there. It's 104, the address. Okay, not 101. C++ is just being nice to you. It's like, all right, you want the next int. That must be what you mean. Okay, so you can do this for C strings as well, because a C string is just an array. And finally, you understand why the type is the type that it is for C strings. They're equivalent. So, sorry to blow your mind a few too many times this week, but that's just what has to happen, I guess. So, if you want to allocate and delete arrays now, you can do that. You can say int star, a pointer to the beginning of this array that I'm about to make on the heap, int star p equals new int, and then you give some brackets, 42. So this makes a new array of ints on the heap and puts the starting address in P. And the one thing you have to watch out for is once you're done with this, like here's your stack, you just made P point to a brand new array of a very long size on the heap. The idea is once you're done with this, C++ doesn't know when you're deleting whether or not you made just one int or 42 of them, because the syntax is the same. You're still if you just want one int, you still assign to an int star. So to tell C++ that I want to delete an entire array that I made for myself, use delete bracket bracket. Okay? P. Deletes the entire array. So you have to say, all right, it's an array that I want to get rid of, not just one int on the heap. Okay? That's all. And that's two brackets together. It kind of messes that up, doesn't it? Let's do that. There we go. So that's all you have to do for arrays. And then the last thing that I want to talk about in this very interesting subsection is memory leaks. So a memory leak is when you lose access to data in your program. So for example, here's the most simple example that I can think of. These lines. Int star I equals new int. Then, I don't know, play around with I, like set it to 42. Then I equals another new int, star I equals 43. So I'm claiming that this is a memory leak. Let me show you. So these variables, this I right here, it lives on the stack inside of whatever function it was in. So we made a variable called I to give a name to the place on the heap that we allocate this int to be. Okay, so I will point to, after the first line, a brand new int, shiny and new, made on the heap. And maybe its address is my favorite address, 100. And so I will hold 100. Oh, sorry, that looks like a 6, doesn't it? 100. Alright, that's all well and good. I can set it to 42, maybe print it out, do cool stuff. Then I can say I equals new int. And every time I say this, I make a brand new place on the heap. So I just made a new box. Maybe this one is address 116. Doesn't have to be in order. And then I set I to be that, which means, oh shoot, I is now 116. So it's now pointing right here. I can set that to be 43. Let me see if I can use other colors. So now it's 116, and it points right here, and we just got rid of that pointer. And I set it to 43. Notice, and it's also shiny and new, of course, because it's on the heap. Notice that I just lost access to this int right here. I have no way of getting to it. I was my only way of getting to this memory location. And I just overwrote I with a brand new place on the heap. So I can only ever delete this one by saying delete I, okay? I cannot delete the first one. So sad. And that's what a memory leak is. Okay? So we've talked about two different kinds of errors. You have segmentation faults, memory leaks. Oh, three actually. You have out of memory as well. So the heap is a nice place, but you have to watch out for not leaking things, not dereferencing memory that's not yours, things like that. But it's really nice for when you don't know how much of something you need. So for example, when you have a vector, well, I'm going to push back. I'm going to make a new spot. I'm going to make a new spot on my vector. I'm going to add stuff to my string. Here's a secret. You've been using the heap for a very long time already. So vectors and strings secretly use dynamically allocated arrays, either of characters or whatever type you needed for your vector, because it needs to grow, okay? Because you don't know the original size, it needs to be able to grow and replace itself. they need to allocate more memory if you push some more stuff to the vector, if you add some more characters to the string. So this is all useful, and it will make sense, I hope. Okay, so we've talked about so many things, and you might be wondering, well, if vectors and strings do this for me, what's the whole point of ever needing to use pointers or heap things myself? And let me give you at least one good answer. And this is the idea of a linked list, and it's something from CSCI 41 is usually where we hit this really hard. So if this seems useful to you, you're going to have to wait another semester to actually get down and dirty with this. But you will read about it a bit in your Xi book, and you'll also, I think, have at least one Xi lab about linked lists, but I won't give you any virtual machine labs on them. And it answers the question like, when will I ever use a pointer over a reference? When should I ever actually use the heap? And let me give you a very lightning intro to linked lists. You'll learn a whole lot in 41 if you take that, but here is what a linked list is in a nutshell. It's a data structure, and it holds these things called nodes. And inside of a node, there is a piece of data, and also a pointer to the next node in the list. Usually, those nodes are made on the heap. Yeah, usually it's fine. And when I say usually, I mean almost always, are made on the heap. And they are, I guess we'll call them a competitor to arrays or vectors. It's easier to do some things with them as opposed to an array. So here is one single node in a linked list. This is a node. It holds a piece of data and then a pointer to the next node in the list. So if I had to hold 1, 2, and 3 in that order, I'd make 3 nodes, and I'd set the pointers in this way. So maybe this was address 100 is the start of this node. This was like 212. This was, I don't know, 256. This one would hold 212. This one would hold 256. And the end of the list is marked with the null pointer. Okay, so don't know if I want to draw arrows anymore. Null marks the end. Okay, so that is a sample linked list, and let me give you an example of when this is very a useful thing. So let's add a new node to the beginning of this thing that I'm calling a linked list. It's actually very simple if I have a pointer to the first node. So let's pretend I had this list, 1, 2, 3. Let me draw it smaller because I want to put something at the beginning. 1, 2, 3. I want to add like a brand new node with 0 in it and make that the front of the list. Well, oh man, is that not hard to do? If I were to use a vector, though, maybe I had a vector called v with originally 1, 2, 3, 4 spaces, but 1 was unused. If I wanted to add a 0 right there to this vector, I suddenly have to shift everything over. This needs to become 3, and this needs to become 2, this needs to become 1, then I need to add my 0 to the beginning. So I had to do so much extra work. I had to move the entire array, and slash vector. They suck at this. So let's add a new node to the beginning of a linked list, and that will be your one example to hopefully get you excited for CSCI 41. So here's what a node looks like. I'll make a struct for them. Each node in a linked list will hold a piece of data. We'll just have it be ints, and then a pointer to the next node. All right? Not too bad, I hope. So each node holds one data element and a pointer to the next node. Okay. Oops, didn't want to do that. Yeah, I guess I have to. And so if I want to allocate the original list, 1, 2, 3, I'll say this. So node star, the node 1 equals new node. Do the same thing for 2 and 3. And then I'm going to set 1's data equals 1, and then similar things for 2 and 3. And then I'll set the next pointers. 1's next is 2, 2's next is 3, 3's next is null, because that marks the end of the list. Okay, so now I have just made in memory this list 1, 2, 3. With 1's next pointing to the 2 node, 2's next pointing to the 3 node. And I can iterate through this. There's a way to do it with like a for loop, like you say. All right, n starts here, then n equals n next. Things like that. That'll swap that to point right here. N equals n arrow next would do that. So there's ways to use this like a vector, but I want to show you how to add something very easily to the beginning without having to shuffle things around, because it's just pointers. So say like the front, I'll say node star front of the list. Well, that's the 1 node right now. Let's add the 0 node. All you need to do is make the node itself, make a brand new 0 node, and set its next pointer. Needs to be the 1 node, and the new front is the 0 node. So we had like front originally pointing here, but we changed it. We're like, no, this is the new front. So just a few lines of code to insert something at the beginning of a linked list, no matter how long it is. Imagine there was a million things in this list. It's just 4 lines of code. Imagine there were a million things in this vector. You'd have to shuffle around 999,999 elements. That would take a long, long time. This is much faster. Okay, so that's one, hopefully a good example of when you'd use the heap and when you'd use pointers. Okay, so this is great power, and with great power comes great responsibility. You're going to mess up a lot when you use pointers, okay? And that is just a fact of life. Oops. I apologize in advance. It's just something everybody has to get through, I guess. One way to survive is to use a debugger. It will save your life. This thing is called GDB. Okay, so what is it? It stands for the GNU debugger. So remember that G++ stands for the GNU C++ compiler. So you're in good hands with these GNU people. And what it does is you run it and it runs your program. It's like a program that runs your program. And it gives you helpful information about it as it runs. So it can tell you the values of your variables, the line numbers where the runtime error happened, if that happens to your program. And it's beautiful. The one thing you have to remember is you compile with -G in addition to all the other things you give to the compiler. -G adds what's known as debugging information, like debugging symbols we sometimes say, to your compiled program, and that will be able to tell you things like line numbers and the names of variables. Okay, so that'll be super helpful. So let me just give you one last example of GDB, and I'll send you on your way now. So let's make a program with a seg fault in it. Okay, so here it is. How do I want to do this? Let's just make it super simple. Int star I equals, I don't know, null pointer. Cout star I. You don't have access to null. We're trying to dereference it. Oh no, we're going to get a seg fault. I guarantee it. We never have access to the 0 address. Oh no, we got a seg fault. whatever shall we do? And you run it again, you always get a seg fault. So maybe you're very confused. Maybe this is a very long program that you just wrote, and you're unsure as to which dereference caused it, and that is very common. So what you do is compile with -g. For this example program, it's going to be g++, standard equals C++ 17 as usual, then -g, you give that, then you give the name of the program as usual. That's fine. Okay, so I'm going to add -g, and I mean, it made the same program. I can still run it. Bam, still get a seg fault. That's not the whole thing, okay? Instead of /segfault, run gdb /segfault. Like, pretend you were running the program and then put gdb right in front of it. Okay? So I say, not /segfault, gdb /segfault, hit enter. It'll pop up inside of gdb. It gave you a lot of information. And now you're at like the terminal prompt for gdb itself. Okay? And here is the things that you can do. You can say R to run the program. BT stands for backtrace to view the stack, and print X prints the value of the variable X in the current stack frame. Okay, these three things will save your life, I promise. So I'm going to go say R to run the program, hit enter, it's like a terminal, and it tells me, oh, we got a seg fault, boohoo, on line 7 of segfault.cpp. Do you see how this will save your life? So it tells me exactly where it happened, which you know the terminal did not. It just said weird error. You can see the line number. You can see the chain of function calls if there were more than one. Oops, sorry, I included that slash on accident. There. There's just main at the moment, but it would tell you more information if there were functions being called on the stack. So it's line 7 is the problem. Cout I. Cout star I, that is. So, okay, something's wrong with line 7. It's using the variable I. What's I right now? In the current program. Print space I, enter. Oh, it was 0. That's null. Print star I? Yeah, we can't access that. That would give us a seg fault. We can't access that memory. We don't get access to that address. Okay, thank you, GDB. Say exit. Oh, sorry. You can say quit. And say yes. Kill the program. Quit. Exit GDB. And so suddenly you know exactly where the program went wrong. You know exactly where, or you know exactly where in the stack you were, which functions called which functions. You know the values of the variables as well, potentially. So this will tell you exactly what went wrong in your program, and I really encourage you to use GDB. Okay, so now on to some exercises, and then you're out of here. So I guess the one really nice exercise, do this as many times as you can, is change an old lab or Zilab or in-class example to use pointers and or the heap. Like, so instead of passing an int, pass addresses of ints and use the pointers. Get used to using the address of operator, get used to using the dereference operator, get used to saying a type name and then put a star to declare a pointer to it. Okay? That will really help you, I think. And of course, I'm going to force you to do it in your lab, but it would be a good starting point to do some things that you already know how to do with pointers now. Okay? So at the very end of the day, we've learned a whole lot about how memory is arranged inside of our computer, and it is a learning experience. This is a difficult topic, so props to you if you got through this set of lectures. Please yell at me if you have any questions, and now you are finally able to understand and laugh at this comic. Okay, so I'll see you in your lab.